Welcome back. In our previous video, we laid the groundwork by understanding what neural networks are and how they work. We also set up our development environment and created our first neural network structure in PyTorch. If you haven't watched that video yet, I highly recommend checking it out first. It will make everything we cover today much clearer. Now comes the exciting part. We are going to bring our neural network to life. In this second part of our tutorial, we will take our model from a simple structure to a fully functioning neural network that can actually learn and make predictions. Think of the previous part as building the brain and this video as teaching it how to think. Here's what we are going to cover. How to prepare and format our data so our network can understand it. Setting up the training process with loss functions and optimizers. Creating an efficient training loop. Visualizing our results to understand what our network has learned. And finally, evaluating our model's performance with real metrics. The best part, we will be using a simple practical example that will help you understand exactly what's happening at each step. By the end of this tutorial, you will have a neural network that can classify data points with impressive accuracy. And more importantly, you will understand how every piece fits together. Let's dive into the practical side of neural networks. Hey guys, so welcome back to this VS Code tutorial. So as usual, we are going to import some functions, starting with importing Torch and NumPy and Matplotlib. Let's run this. Cool. We defined these two functions and I explained these two functions in my previous tutorial. And what it does is that it checks if you have MPS, which is Apple Silicon GPU installed. So if you have Apple Silicon GPU, it will use that as a device. Otherwise, it will fall back to the default option, which is a CPU. If I run this block, you see, because I'm using Apple Silicon GPU, cool. So the next is we define a simple neural network. And in my previous video, we laid the foundation. We defined how to define a simple neural network. Just to rephrase very quickly, when you define a class, we inherit from nn.module class, and then we define init method. In init method, we define the layers. So here we are defining an input layer with 2 features. We define hidden layers with 5 neurons and an output layer with 1 neuron. Then in the forward class, we define how the data should flow through the architecture. So let's run this. And the first thing we need to do is the data preparation. And here we are defining this data. So we are creating a synthetic data. We are creating 500 random samples with 2 features. And we define the classification rule. So this is the decision boundary. So x plus y is equal to 0. All the points above this boundary are classified as 1. And all the points below that boundary is classified as 0. So we create 2 classes. We need to convert this x and y into PyTorch tensor. The way we can do is using the command torch.float tensor. And to device is a convenient way to write and tell your program that use the GPU if you are using GPU, otherwise CPU. Okay. So run this block. Cool. So now let's have a look at the data. So as you can see, we have 2 classes, class 0 and class 1. Class 1 is our blue points, and we define class 0 by red points. And so this data we will use for our training purpose. The first thing, the training setup, the first thing you need to do is define the model. So you initiate the class of the model. So here we have the simple NN. And as you can see, and you will keep seeing that I will be using 2 device. It's a good convention. Then you define the loss function. Okay, so here we are defining NN dot BCE with logits loss. BCE stands for binary cross entropy loss, and this is the standard loss function we use for classification or binary classification tasks. So let's discuss what it means. The loss function is like a feedback system that measures how far off our network's predictions are from the true values. When we use BCE with logits loss, binary cross entropy with Logit's loss, we are specifically measuring the error in binary predictions, where our network needs to decide between two classes like 0 or 1. Think of it as measuring the cost of being wrong. The bigger the mistake, the higher the loss value. Why this specific loss function? Let me break it down. The BCE part measures how confident our predictions are and how wrong they are. The with logits part includes a special function called the sigmoid function that helps keep our predictions between 0 and 1. And lastly, it's perfect for binary classification tasks like ours. Okay, so after you define the loss function, we need to define the optimizers. And here we are using optim.sgd. SGD stands for stochastic gradient descent. The input of this function is model.parameters. So the model.parameters are the parameters of the neural network we defined. And the learning rate, 0.01. Let's discuss what this optimizer does. If the loss function is the teacher grading the test, then the optimizer is like the study strategy. We are using stochastic gradient descent here, and that learning rate 0.01 is super important. It's like deciding how big of adjustment to make when you are learning from mistakes. PyTorch gives us a lot of options here. For simpler problems, MSE loss, mean squared error, works great. For multiple classification problem, use cross entropy loss. If you need faster learning, the Adam optimizer is very popular. And if you're dealing with tricky changing patterns, try with RMS Pro. We are keeping it straightforward with BCE, with Logit's loss and SGD because they work well for binary classification and are easier to understand. As you get more comfortable, you can experiment with more combinations. Okay, so after you define the optimizer, the next part is to define the training loop. So now first thing you need to do is define the for loop. And here we are defining 5,000 epochs. So we are essentially saying that the network will learn the parameters 5,000 times. The first thing we need to do is define outputs is equal to model. So you provide the X tensor, which is your input training data, to the model, and it will give you some predictions, the output. Then using the loss function, you calculate the loss function. Then you say optimizer.zeroGrad, and zeroGrad is important because if you specify zeroGrad, that means that after each epoch, the optimizer will initialize the gradient to 0. Otherwise, it will just keep accumulating. That's just a thing in PyTorch. Then you do the loss backward. So once you define the loss, you go backward, back propagation. So you say loss.backward and optimizer.step. Then you at each epoch, you keep your losses into an array function. You append losses.append. Losses is just an array of loss. And it will be easier for us to see the learning, the loss going down after each iteration. Okay, let's run this. Okay, now it's done. And after 5,000 epochs, the loss is 0.046. You see the loss starts from here, and then every epoch it's decreasing. And this is the figure. Let's discuss this. Let's look at how our neural network learned over time. This graph shows the training loss. Think of it as the network's error rate over 1,000 epochs or training iterations, starting from around 0.8-ish, and then it goes down to around 0.04. The curve flattens out, and it suggests that our model has found a good solution and further training might not improve it much. Okay guys, so after the training, the next part is the model evaluation. We need to see if our model is good enough to predict. And this is the code, and I'm going to share this notebook with you so you can have a look, but I will discuss the results with you. This is the decision boundary plot, and this visualization shows how our neural network makes decision. The background color represents the two classes, yellow for class 1 and purple for class 0. The dotted line is our decision boundary. It's where the network switches from predicting one class to the other. The dots show our actual data points, blue for class 1, red for class 0. Notice the X mark here. The X marks, these show where our model made mistake. The fact that we see very few X marks suggests our model is performing really well, and most errors occur near the boundary where the classes overlap. Finally, let's examine our model's performance in detail. The confusion matrix shows us exactly how well our model is doing. Looking at our metrics, 99.60% accuracy means we are correctly classifying almost all cases. 100% precision means when we predict class 1, we are always right. 99.18% recall means we are finding almost all actual class 1 cases. The F1 score of 99.59% shows we have a great balance of precision and recall. These numbers confirm what we saw in our decision boundary plot. Our neural network has learned to separate these classes very effectively. We have successfully built and trained our first neural network in PyTorch. Let's summarize what we have accomplished. We created a simple neural network that learned to separate two classes. We achieved excellent performance with over 99% accuracy. And we visualized how our model makes decisions with a clear boundary. We learned how to evaluate model's performance using multiple metrics. But this was just the beginning. In our next tutorial, we will tackle a more challenging problem. We will see how to learn the non-linear classification problem. You will see how to handle data that can't be separated by a straight line. The skills you have learned today, building models, training them, and evaluating their performance will be the foundation for handling these more complex scenarios. Thank you for following. And if you have liked this video, please give it a like and subscribe to my channel and stay tuned for the next tutorial. Until then, take care and bye.